Okay, guys, I had an issue. I had to kind of start over. Then I had another issue with the recording. All right, so we're doing the Archimedes principle. All right, so that shows us the buoyant force is the net upward force on an object in any fluid. Okay, so there's going to be a net upward force on the object in any fluid. And here's the way you calculate the buoyant force. The buoyant force, real simply, is equal to the rho of the water that it's in, okay, of the fluid, the rho of the fluid that it's in, times the volume of the object, okay, times the volume of the object times g, okay. So here's what I've got. This is a little thermite ball, all right. It's made out of thermite, and we clack them together. I think I'm kind of running out of things, so I may not get a spark here. Oh, you can kind of hear it spark. I made a mess on the page. But anyway, so I got this little thermite ball, and I went and weighed it, or I found its mass, and the mass of it is equal to 129 grams, which is equal to 0.129 kilograms. So what's its weight? The weight in air, is equal to mg, which doesn't come out to be much. I'll be honest. I mean, it came out to be 1.26 newtons. It's not very heavy. Okay, 1.26 newtons is not very heavy. We need to make this even bigger. I apologize. I knew something was wrong. There we go. That's much better. All right, so 1.26 newtons. All right, and yeah, there's a little mark there. That's one. Okay, so it's 1.26 newtons. Now, what's its weight in the water? Now I'm going to put it in the water. Or let's say I was picking this thing up at a constant speed. All right, so let's say I have my little thermite ball, and now we're doing it in air, and I'm picking it up at a constant speed, so I got a tension going this way, mg going this way. So some of my forces in the y direction are equal to 0 because acceleration is equal to 0. It's going at a constant speed as I'm lifting it up. So I've got T minus mg. So the tension in the rope. Now, what's going to be, so let's put it in water. And let's try and lift this thing. I'm going to lift it at a constant speed. Okay, it still has mg. Earth is still pulling on it. But wait, there's more. There's a little buoyant force pushing up on it this way. Aha! So up here, my tension is equal to mg. Okay, but down here, some of the forces, again, it's going at constant speed. Some of my forces, T, plus F of B, that one's going up here because here's my tension force, minus mg is equal to 0. So the tension is equal to mg minus F of B, so that makes it a little bit less. But how do I compute F of B? Well, I know that what I did was I found that the density of thermite, is equal to 3,000, based on my own calculation. I kind of 3,225 kilograms per meters cubed. So I know the density of the thermite. I know the mass of the thermite is 0.129 grams, but I don't know the volume of the water that it displaced. But wait a second, I do too, because I know that density is equal to mass over volume. I've got this number and this number. I think I can get this guy right. And that would be the volume of the water displaced. So the volume is going to be really small because it's going to be 0.129 kilograms over 3225 kilograms per meters cubed. But look what happens. The kilograms cancels. The meters cubed goes up there. Yes, and that's what I calculated to be earlier. Yes, all right, good. Because I put it in a beaker and measured it, and it came out to be 40 milliliters or 40 cc's, which is, so its volume is 4.0 times 10 to the negative 5 meters cubed. Okay, so now I've got the buoyant force. So now I can compute the buoyant force, which is pretty straightforward now, because the buoyant force is equal to, if it's in regular water, that'd be 1,000 kilograms per meters cubed. Now watch what happens. Watch what happens. 1,000 because this is the row of the fluid, row of water. And now what I said, yeah, up here, the buoyant force. Now times 4 times 10 to the negative 5 meters cubed. Hey, look what happens here. Bang, bang. That is way cool. Now I'm down to kilograms too. And times 9.8 meters per second squared. Notice I got a mass times acceleration, so that's a force. And that's a positive force. And that's going up. And then the rest, you all can finish. I mean, well, except I got to finish it now. Because these are actual objects that I found and that I actually took the 0.392 newtons. This is when we'd probably be working in dynes. For you chemists like to work in dynes because you work with smaller stuff. And so the new tension is the old mg, which is 1.296 minus, so the tension prime is equal to mg minus the buoyant force, which was 1.26 minus 0.392. And so if I could do it, but I don't want to ruin the, I couldn't get the beam back, or it was that little electronic accelerometer basically is what I was using. 1.26 minus the answer, 0.868 newtons. So it's lighter. The tension is less. All right, we'll go on to the next type of problem. What are we going to do?